My name is Vikrant Jain, and this is my Physics 2211 Lab 5 presentation of projectiles and energy as the focus of my video discussion. The idea behind Lab 5 was to incorporate different concepts that we learned throughout the semester to assure a higher understanding of them. And so for my decision, I decided to create a lab video involving a combination of projectile motion, the impact of kinetic energy and gravitational potential energy, the energy principle, and a short discussion on the conversion of energy units from joules to calories and how that relates to real-life elements. So now let's dive into the introduction of my video. The content displayed through Tracker will analyze the arc-like motion of my basketball as it is kicked through the air. In terms of the computational model, the primary tools used were Newton's second law and the energy principle in order to both map the ball's arc-like motion and also gain a higher understanding of the change in energy involved as it moves. Then I moved into comparing my projected data with my experimental data and mapping the differences and similarities between the two. Afterward, the conversion from joules to calories were explored through the incorporation of a conversion component within the Python code to illustrate this relationship. Lastly, the total calories involved were displayed in the motion of the ball based on the change in energy. There were several key concepts to note before diving into the analysis of the ball's motion. The most fundamental, obviously, is the change in position, which is delta x equals to initial velocity times delta t plus 1/2 at squared. The Newton's second law was also key in terms of the final velocity equaling initial velocity plus acceleration times time, and acceleration equaling the net force over the mass of the system, which in this case was the basketball. Now comes the more advanced concepts involved in this lab. The kinetic energy equals 1/2 mv squared, and potential energy was seen to equal the mass of the system times gravity times the height reached. The energy principle is also very significant, as the total energy equals the kinetic energy plus potential energy. And this was key, as you can see here, in terms of, for this lab, the total energy equaling 0, and thus the change in potential energy and kinetic energy being set as equal to one another. Now let's focus on the initial conditions using the Python code. As you can see here, the mass of the ball was set to equal 0.624 kilograms, and the position of the ball was not set as 0, 0, 0 because the position of the ball did not initially start at the origin. As you can see in this Tracker video, it had a y component that started above 0, and that is why its position is seen to equal 0.21 for the y component and close to 0 for the x component in terms of 0.009. The ball was also already in motion, which is why the initial velocity was set as 2.45 for the x component and 3 meters per second for the y component. Now let's see the arc-like path the ball takes through Tracker. By graphing this data through Tracker, we can see here both the x direction of the ball's motion and the y direction of the ball's motion, and it's very important to note the difference in shape between the two components, as the x component follows a linear line and the y component has more of a parabolic shape, and that is because the velocity in terms of the x component does not change for the ball, and the y component, the velocity does change because of the gravitational force acting on it. This was a very key concept to know when creating the computational model. As you can see here, both all the key fundamental concepts that we discussed earlier were really key in order to form the computational model and make it accurate. Here we can see the computational version of the equation we discussed earlier for kinetic and potential energy, and here we can see that the force of the gravity in terms of vector form is 0 in all components except the y component, which is set equal to the mass of the ball times gravity in the negative direction. Near the bottom, we can see the change in kinetic energy and potential energy also being calculated in the code. Now when we run the computational code and we see the computational model and juxtapose it to the real data, we can see that the similarity between the two is very strong, and thus can say that the computational model was created successfully. The ball follows the same parabolic shape that it does using the real data, thus showing a successful incorporation of Newton's second law. Now back to energy. Here we can see the computational model used for converting joules to calories. The conversion factor was set to 4.20 because 1 calorie equals 4.20 joules. Because the ball's velocity in the x direction remained constant, we can see here that the x direction kinetic energy was set to equal 1/2 ball's mass times 2.45, which was the initial velocity, squared. However, we know that the ball's velocity is not constant in the y direction, which is why the y direction gravitational potential energy was shown here to equal the mass of the ball times the constant g, which is 9.8 meters per second squared, times the highest point that the ball reached during its arc-like motion, which was 1.079 meters. By adding these two energies, we were able to get a total joule value, which we divided by 4.20 to convert it to calories, which we got as a resulting value to be 2.017 calories. To get an idea of its significance in terms of a real-life situation, we can compare it to the calories in a Big Mac, which has 550 food calories, which is equal to, because it's food calories and not the calories we discussed here, when we convert it, it equals to over 272,000 repetitions of the ball's motion to attain the same value in terms of food calories, because 1 food calorie equals 1,000 calories. So in conclusion, we can note that Newton's second law and energy principle were successfully incorporated into the lab experiment through the analysis of the arc-like motion of the basketball, and the energy conversion from joules to calories successfully illustrates the relationship between the two forms of displaying energy and their significance in real-life situations.